Okay, well, welcome back to software engineering. We're continuing to get through our main section here in covering all of the introductory items in the software engineering, which end up being fairly comprehensive. And for this lecture, we're going to be talking about design and implementation. So the main things that we'll be covering here are object-oriented design using unified modeling language. We'll talk about design patterns, implementation issues, and open source development. So for design and implementation, software design and implementation is a stage in the software engineering process at which an executable software system is developed. Software design and implementing activities are invariably interleaved. So software design is a creative activity in which you identify software components and their relationships based on a customer's requirements. And then finally, implementation is a process of realizing the design as a program. So a common thing that you end up thinking about is, do you build or do you buy? Do you create some new code, or you just buy something off the shelf? So in a wide range of domains, it is now possible to buy off-the-shelf systems, that is COTS, commercial off-the-shelf, that can be adapted and tailored to the user's requirements. For example, if you want to implement a medical record system, you can buy a package that is already used in hospital. It can be cheaper and faster to use this approach rather than developing a system in a conventional programming language. When you develop an application in this way, the design process becomes concerned with how to use the configuration features of that system to deliver the system requirements. So let's talk about object-oriented design and how we can do that with unified modeling language. So an object-oriented design process is a structured thing that involves developing a number of different system models. They require a lot of effort for development and maintenance of these models. And for small systems, this may not be cost effective. However, for large system development by different groups, design models are an important communication mechanism. So what are the stages of the process? There are a variety of different object-oriented design processes that depend on the organization using the process. Commonly, the activities include defining the context and modes of using the system, designing the system architecture, identifying the principal system objects, developing design models, and finally specifying object interfaces. So the process illustrated here is using a design for a wilderness weather station. So that's one of the common designs that we keep coming back to as we go through our material here. So in terms of the system context and interactions, understanding the relationship between the software that is being designed in an external environment is essential for deciding how to provide the required system functionality and how to structure the system to communicate with the environment. Understanding of the context also lets you establish the boundaries of the system. Setting the system boundaries helps you decide what features are implemented in the system being designed and what features are in the other associated systems. So for context and interaction models, a system context model is a structured model that demonstrates the other systems in the environment of the system being developed. An interaction model is a dynamic model that shows how the system interacts with the environment it is used. So here's a context for the weather station. And so we have a variety of different things that you have the weather information system, you have control, you have a satellite component, and these feed into up to N weather stations that are deployed to create this whole complement of capability for weather monitoring. Here's the use cases. And so we have a couple of individuals. We have the weather information system, and then we have the control system. And so the interfaces that the operator would have engaging with the weather information system is that you could have the report the weather, report the status. And in the control system, there's various functions that you can have: restart, shut down, reconfigure, power save, and remote control. So let's talk in more details about the use case description for report weather. So the actors are the weather information system and the weather station. And so the weather station sends a summary of the weather data that has been collected from the instruments in the collection period to the weather information system. The data sent are the maximum, minimum, and average ground and air temperatures, the maximum, minimum, average air pressure, and the maximum, minimum, and average air speeds. The total rainfall and the wind direction is sampled at 5-minute intervals. So the stimulus is the weather information system establishes a satellite communication link with the weather station and requests transmission of the data. So it's stored and then periodically offloaded to satellites. And in response, the summarized data is sent to the weather information system, and the weather stations are usually asked to report once per hour, but this frequency may differ from one station to another and may be modified in the future. So what about architectural design? Once interactions between the system and the environment have been understood, you use this information for designing the system architecture. You can identify the major components that make up the system and their interactions, and then you may organize the components using an architectural pattern, such as a layered or client-server model. The weather station is composed of independent subsystems that communicate by broadcasting messages on a common infrastructure. So here's a high-level architecture of the weather station. And so all these are connected with a communication link. So you have fault management, configuration management, power management, so various types of management subsystems. And then you have the systems to help make that happen. You have the communication, you have the data collection and instruments. And so a variety of different subsystems are all connected with a communication link. So in terms of the architecture of the data collection system, and so you have the receiver, the weather data, and then the transmitter. So you have to receive the data, then transmit it when it is requested and when there's assets that are available to take that data that's trying to be passed on. So what about object class identification? Identifying object classes is often a difficult part of object-oriented design. There's no, quote, magic formula for object identifiers. It relies on skills and experience and domain knowledge of system designers. Object identification is an interactive process. You are likely to get it right. You are unlikely to get it right the first time. So it's something to think in mind. It's okay to have an iterative process. So in terms of approaches to identification, you can use a grammatical approach based on natural language design of the system, based on the identification of tangible things in an application domain. You can use a behavior approach and identify objects based on what participates in what behavior. And you can use a scenario-based analysis. The objects, attributes, and methods in each scenario are identified. So what about the weather station object classes? Object class identification in the weather station system may be based on the tangible hardware and data in the system. So you have the ground thermometer and altimeter and barometer. So the application domain objects here are hardware and objects related to the instrument to the system. For the weather station, the basic interface of the weather station is the environment. It's therefore reflects the interaction identified in the use case model. And finally, the weather data. And it encapsulates this summarized data from the instruments. So here is spelling this out in terms of the weather station object classes. And so you have the weather station, you have the weather data, ground thermometer, altimeter, and barometer. And so you can interrogate each one of these meters, and there's different things that are available that you can get. And plus for the weather station, you can have multiple weather stations, and you can be getting the weather data as desired. So In terms of design models show the objects and object classes and relationships between these entities. There are two kinds of design models, structural and dynamic. So the structural model describes the static structure of the system in terms of object classes and relationships. And the dynamic model describes the dynamic interaction between objects. So what are some examples of design models? Subsystem models that show logical grouping of objects into coherent subsystems. You can have sequence models that show the sequence of object interactions. You can have state machine models that show how individual objects change their state in response to events. And finally, you can have other models that include use case models, aggregation models, generalization models, etc. So a variety of different ways you can be using design models. For subsystem models, it shows how the design is organized into logically related groups of objects. In the unified modeling language, these are shown using packages and an encapsulation construct. This is a logical model. The actual organization of objects in the system may be different. For sequence models, it shows a sequence of objects interactions that take place. Objects are arranged horizontally across the top. Time is represented vertically, so models are read top to bottom. Interactions are represented by labeled arrows. Different styles of arrows represent different types of interactions. A thin rectangle is the object lifeline, represents the time when the object is in the controlling the controlling object in the system. So here's an illustration of a sequence diagram describing the data collection in the weather system. And so you request data, you get an acknowledgement, okay, that it understands that you have a request. The SATCOM can then go interrogate the weather station to ask that they would like to get that weather, and it acknowledges that it receives that request. It goes ahead and gets a summary, that the summary is generated. It then sends a report. The comm system acknowledges that it got that, and finally it replies that a report has been sent, and then it gets acknowledgement. So there's nice two-way handshakes between each of these data collection elements. So for state diagrams are used to show how objects respond to different service requests and the state transition triggered by these requests. State diagrams are useful high-level models of a system of an object's runtime behavior. You don't usually need a state diagram for all the objects in the system. Many of the objects in a system are relatively simple, and a state model adds unnecessarily details to the design. Here's an illustration of a state machine for the weather station. And so you start out with in the shutdown mode. You then can go into various types of modes. First of all, configuration, self-test, or maybe going into a safe mode. But once you finally go into operation, that's what you have in this blue part of the figure, that it's in operation. And so you can be in running, collecting, summarizing, transmitting, and testing modes. And this is the various relationships between each of those states that the weather station can operate in. In terms of interface specification, object interfaces have to be specified so the objects and other components can be designed in parallel. Designers should avoid designing the interface representation, but should hide this in the object itself. Objects may have several interfaces, which are viewpoints of the methods provided. The UML use case diagrams for interface specification, but Java may also be used. So you can get more specific than just using universal modeling language. You can get into the specifics for developing classes and whatever in Java. So here is looking at the interfaces for the weather station. So you have reporting and control, and there's various things that you can be requesting from the weather report. You can identify, you can get the status of the the weather station for remote control. You can also do various things as well and get information back. So we already have talked about design patterns before, but now we're getting into how that would play out in the use as you're developing a system. So a design pattern is a way of reusing abstract knowledge about a problem and its solution. A pattern is a description of the problem and the essence of the solution. It should be sufficiently abstract to be reused in different settings. And pattern descriptions usually make use of object-oriented characteristics such as inheritance and polymorphism. So patterns and pattern languages are ways to describe best practices, good designs, and capture experience in a way that is possible for others to reuse this experience. So you don't have to reinvent the wheel every time you start a design. So in terms of the pattern elements, there's a name, problem description, solution description, and consequences. And so these are the various things that you want to be including in a pattern. And so as an example for the observer pattern, so the name is observer, the description that separates the display of object states from the object itself. And so for the problem, it's used when multiple displays of states are needed. And the solution is to see, well, you want to see the slide with UML description. So we have that contained here in our presentation. And the consequences, optimizations to enhance display performances are impractical. So you need to have multiple ways of displaying data based on what is necessary. So here are the supporting details, a couple charts. And so you separate the displays of the state of an object from the object itself, allows alternative displays. And so in many situations, you have to provide multiple displays of states. And so you could have different modes that you're operating in. And so this allows for you to be able to manage that. So what is the solution description? This involves two abstract objects, the subject and observer, and two concrete objects, the concrete subject and the concrete object, which inherit the attributes of the related abstract objects. The abstract objects include general operations that can be applicable in all situations. So won't read all of this, but this just gives you some more information about how that works for the observer pattern. So here is an illustration of the multiple displays that you could have in the observer pattern. And so maybe a pie chart might be useful in some situations, and then a bar graph might be more beneficial in others. And so this would give you the ability to look at that in the way that is best deemed useful at the moment for the user. So here's a UML model of the observer pattern. And so you have the subject and the observer. And so those are fed in by the concrete subject and the concrete observer. And so that's what we're seeing laid out in this UML top level model. For the design problem, to use patterns in your design, you need to recognize that any design problem you are facing may have an associated pattern that can be applied. You can tell several objects that the state of some other object has changed. So that would be the observer pattern. To tidy up the interfaces to a number of related objects that have often been developed incrementally, that would be the facade pattern. Provide a standard way of assessing the elements in collection, irrespective of how the collection is implemented. That would be the iterator pattern. Finally, allow for the possibility of extending the functionality of an existing class at runtime. That would be the decorator pattern. What about implementation issues? The focus here is not on programming, although this is obviously important, but on other implementation issues that are often not covered in programming text, reuse, configuration management, whose target development. So most modern software is constructed by reusing existing components. And so we have to be thinking about reuse. For configuration management during the development process, you have to keep track of the many different versions of the software components in the configuration management system. Finally, targeted development. Production software does not usually execute on the same computer as a software development environment. Rather, you develop it on the one computer, the host system, and execute it on a separate computer, the target system. So you have to keep that in mind. What is the performance and the capability of the target system that will finally be used? Okay, from the 1960s to the 1990s, most new software was developed from scratch, written by all by writing all code in a high-level programming language. The cost and schedule pressure means that this approach became increasingly unviable. An approach to development based around the reuse of existing software emerged and is now generally used for business and scientific software. So for reuse level, there's the abstraction level, the object level, the component level, and the system level. For the abstraction level, at this level, you don't reuse software directly, but use knowledge of successful abstractions and the design of your software. At the object level, you directly reuse objects from the library rather than write the code yourself. At the component level, components are collections of objects and object classes that you reuse in application systems. Finally, at the system level, you reuse the entire application systems. So here is just a summary of that, the various kind of things that you could be doing for reuse. You can be using commercial off the shelf, just import a system. You can have components that you select from a component framework. You can have objects that you use programming language libraries, and so you can just call on those libraries when you need it. Finally, you can have abstraction with architectural and design patterns. In terms of cost for use, the cost of the time spent in looking for software to reuse and assessing whether or not it meets your needs. Where applicable, the cost of buying the reusable software. For large off-the-shelf systems, these costs might be very high. The cost of adapting and configuring the reusable software components or systems to reflect the requirements of the system that you are developing. And you then considering that the cost of integrating reusable software elements with each element if you are using software from different sources and with the new code that you have developed. In terms of configuration management, configuration management is the name given to the general process of managing a changing software system. The aim of configuration management is to support the system integration process so all developers can access the project code and documentation in a controlled way, find out what changes have been made and compile it and link the components to create a system. And for more details, one can look over at chapter 25. For configuration management activity, there's version management, there's system integration, and there's problem tracking. So version management is where the support is provided to keep track of the different versions of software components. Version management systems include facilities to coordinate development by several programmers. System integration is where support is provided to help developers define what version of the components are used to create each version of a system. This description is then used to build a system automatically by compiling and linking the required components. Finally, problem tracking is where support is provided to allow users to report bugs and other problems and to allow all developers to see who is working on these problems and when they are fixed. So here's a configuration management tool interaction. And so you have the component versions, you have the system version, and you have the system releases. And so each one of these things that for going from components to a version, you need to be considering the system build and the version management, that what you're thinking about. And as you start to come up with system releases, you have to be thinking, well, what change proposals are going to be put into this release? What is the tempo of your release management? And then you finally have system releases on a periodic basis. For host target development, most software is developed on one computer but runs on a separate machine. More generally, we can talk about a development platform and an execution platform. Platform is more than just hardware. It includes the installed operating system plus supporting software, database management system, and for development system, an interactive development environment, or IDE. Development platforms usually have different installed software than execution platforms, so these platforms may have different architectures, and so that has to be considered. So you have the host target development, and so here is the development host, and so you have your integrated development system, compilers, and testing tools. And then when you move to a target, that the software is downloaded or transferred to the target. And so on the execution platform, it uses libraries, related system, and databases to operate as it's meant to perform. For development platform tools, and integrated compiler and syntax-directed editing system that allows you to create, edit, and compile code. So this is something that you're going to have as part of your tools. You have a language debugger system. You have a graphical editor tools, and such as tools to edit the UML models. You have testing tools that can automatically run a set of tests on a new version of a program. And finally, program support tools that help you organize the code for different development projects. For integrated development environments, software development tools are often grouped to create an integrated development environment. An IDE is a set of software tools that support different aspects of software development within some common framework and user interface. And IDEs are created to support the development in a specific programming languages such as Java. The language IDE may be developed specifically, or maybe an instance of a general purpose IDE with specific language support tools. So in terms of component/system deployment factors, if a component is designed for a specific hardware architecture or relies on some other software system, it must obviously be deployed on a platform that provides required hardware and software support. High availability systems may require components to be deployed on more than one platform. This means that in the event of platform failure, on an alternative implementation of the components is available. If there is a high level of communication traffic between components, it usually makes sense to deploy them on the same platform or on platforms that are physically close to one another. This reduces the delay between the time a message is sent by one computer is received by another. So what about open source development? Open source development is an approach to software development, which is source code of a software system is published and volunteers are invited to participate in the development process. So kind of a cool thing that has been around for a while now. Its roots are in the Free Software Foundation, which advocates that source code should not be proprietary, but rather should always be available for users to examine and modify as they wish. Open software extends the idea by using the internet to recruit a much larger population of volunteer developers. Many of them are also users of the code, so they have an interest to make sure the code is working quite well. The best known source product of open source is something called the Linux operating system, which I'm sure you're probably familiar with. And it's widely used as a server system and increasingly as a desktop environment. Other important open source products are Java, the Apache Web Server, and the MySQL database management system. So what are some of the issues with open source? Should the product that is being developed make use of open source components? And should an open source approach be used for the software's development? There's things that are both benefits and maybe some liabilities, depending on where your point of view and what you're trying to do with your software. For open source business, more and more product companies are using open source approaches to development. The business model is not reliant on selling a software product, but on selling support for that product. They believe that involving the open source community will allow software to be developed more cheaply, more quickly, and will create a community of users for the software. Even Microsoft has moved into embracing open source software as part of their ecosystem. So for licensing, a fundamental principle of open source development is the source code should be freely available This does not mean that anyone can do as they wish with the code. Legally, the developer of the code still owns the code. They can place restrictions on how it is used by including legally binding conditions under this open source software license. Some open source developers believe that an open source component is used to develop a new system, then that system should also be open source. Others are willing to allow their code to be used without this restriction. The development system may be proprietary and sold as closed source systems. So there's different variants of open source that are out there. And so here are 3 examples. The GNU General Public License. This is called the reciprocal license. That means that if you use open source software that is licensed under GPL, then you must make that software open source. The lesser general public license is a variant of the GPL license where you can write components that link to open source code without having to publish the source of these new components. And finally, the Berkeley Standard Distribution, BSD. This is a non-reciprocal license, which means you're not obligated to republish any changes or modifications made to the open source. You include the code in proprietary systems that are sold. And Mac OS is an example of that. In terms of license management, you want to establish a system for maintaining information about open source components that are downloaded and used, be aware of the different types of licenses and understand how the components is licensed before it is used. And you want to be aware of evolution pathways for components. Educate people about the use of open source and have auditing systems in place. And it makes sense to participate in the open source community if you're leveraging what is available there. Okay, well, just to finish up, just a few charts. Software design and implementation are interleaved activities. The level of design and the level of detail in the design depends on the type of system and whether you're using a plan-driven or agile approach. The process of object-oriented design includes activities to design the system architecture, identify objects in the system, describe the design using different object models, and document the component interface. A range of different models may be produced during an object-oriented design process. These include static models, which consist of class models, generalization models, association models, and dynamic models, which include sequence models and state machine models. Component interfaces must be defined precisely so that objects can use them. The UML interface stereotype may be used to define the interfaces. And to finish up here, when developing software, you should always consider the possibility of reusing existing software, either components, services, or complete systems. Configuration management is a process of managing changes to an evolving software system. It is essential when a team of people are cooperating to develop software. Most software development is this host target development. You use an integrated development environment on a host machine to develop the software, which is transferred to a target machine for execution. And finally, open source development involves making the source code of a system publicly available. This means that many people can propose changes and improvements to the software. Okay, that's it for this lecture. Thank you very much. Have a nice day.